That's better. We'll be talking about the web logs on Amazon Redshift project. And then Summer's going to talk about how we designed a petabyte on Redshift, some of our best practices that we used throughout the year we did this. And then we'll have conclusion and questions. So, quick overview. The Amazon Data Warehouse. This is the Amazon corporate data warehouse. So this is where all the data resides for orders, shipments, tax records, etc., used throughout the entire company. It's literally petabytes of data. The primary data warehouse is Oracle. We've been at Oracle for over a decade now. We're also using EMR, and for the past 2 years, we've been using more and more Redshift. We own and manage all of the hardware and software, and aside from the Oracle database, everything is our own IP built from the ground up. One thing I do want to say, it is a bit confusing, is we're not actually part of AWS. So we're part of the corporate side of Amazon that you're used to for buying and selling stuff, as opposed to AWS. So we're the first customer, internal customer, as you will. I always like to start this talk with the elephant in the room. So even though we're part of Amazon, again, we're not part of AWS. So our mission here is to provide the best customer, or to provide customers the best value. All right. We want to leverage Redshift where it will provide the best value. And a big thing here is we like to go first. And I say this: we go first, so you don't have to. We're the first group to get a petabyte on Redshift, and we encountered many problems along the way. Work closely with the Redshift team so that when you do this, it works much more smoothly. We also want to publish best practices, and the goal is satisfied customers. So if it's leveraging AWS technology, great. If it's not, that's okay too. We push them to be the best, and we hold them accountable and hold them to high standards so that they get better. All right. Now, one thing is, this is true. We're standing up here saying what great stuff it is. We do understand the conflict of interest. Happy to take your questions afterwards about that and go deeper. All right, so let's talk about the project here. This is putting web logs, classic web logs on Redshift and how we're doing about it. So first off, why are we doing this? For people who run any kind of web services, bread and butter. The web logs are key for Amazon. They tell us what our customers are doing. If customers are browsing on web pages, on item pages, but not buying things, that's information we need to know to figure out why. For the entire digital space, Kindle, etc., it's turning into more of a classic web e-commerce company. So again, understanding what people are doing with web logs is critical. What makes Amazon unique in this situation is for most online companies where it's just a web presence. So for example, a search engine, you come, you click, might be an ad, might be a search result, and you go away. For Amazon, you come, you place an order, you go away. There's an entire workflow that happens in processing that order for the customer. The item has to go to a fulfillment center. Somebody has to get the item from a shelf, put it in a box. Box has to go get a label, has to go onto a carrier. The carrier has to deliver it. All this stuff is tracked, right? And we make very sure that it gets to the customer. But then we have to make sure we can join that all back from the web clicks. So we're joining these huge logs with lots of transactional data. And our size makes this challenging. We're about 2 terabytes of data per day. That's growing at 67% year over year. So you can think of that. It will be 3 terabytes next year, 4 terabytes the year after that. So what are our goals here? We set up some pretty aggressive goals based on our current performance. So we want to be able to query 2 years worth of web logs in under an hour. Okay? Right now with our existing systems, we're talking more like days. So the goal was 2 years in an hour, which means somebody can actually do a couple experiments during a business day. That's the critical point. We want to make sure we've got constant query time, right? And what that means is as our data grows, 67% year over year, we can scale out the cluster, right, and still deliver results by a wall clock time. So, for example, we do web labs fairly consistently. We want to make sure that web lab data is delivered for people who want to analyze that when they get into the office every morning about 8 o'clock. Finally, timely data, right? We want to make sure that the data is fresh. So our goal here was we want to make sure that all the yesterday's data is available by 4 a.m. So we got a 4-hour window to get it in and process it. Eventually, we want to get to this to be near real time, where it's n minutes old, where n is under 60. Right? So our next goal will, in fact, be 1 a.m., and then we're going to ratchet that down as well. So let me give you some specifics and some hard numbers that we challenged the AWS Redshift team with. For daily data, we wanted to maintain a peak of 5 billion rows, load that in under an hour. All right? For backfill, this is when we correct data. Turns out this happens about 6 times a year. There will be errors in the data, for example, incorrect IPs or missing data that have to be corrected. All right? So we want to be able to handle 1 month of backfill in a day. All right? The third thing, and this is also critically important, we want to make sure that we have what we call cap retention. So we auto-drop old data. Largely for cost constraint, we don't have infinitely growing data. So as data gets old, 2 years old, we no longer care about it, automatically drop it. Okay? And finally, zero impact maintenance. So we don't want to have maintenance windows where we have to take things down to do things. It's always up. It's always operational. Okay? Now, the bottom 2 things, cap retention and zero impact maintenance, we already have those. And so the goal for the Redshift team was to make sure that we kept them with the new architecture. So existing solutions. Let's talk about those so you can kind of understand the baseline of where we went from. So again, our main database cluster is Oracle RAC. We've got 15 months worth of weblogs stored there. Scan rates, and these are big clusters, 32-node clusters with some pretty impressive enterprise-grade SAN. We can do 1 week in about an hour, right? What that translates to, because customers have to chop this up, is it takes them on the order of 1 to 2 weeks to actually do a 15-month scan, right? Because you're scanning not only every row, but every column. So it's massive amounts of data, all right? We also have a number of teams within Amazon who use EMR. So they're using Pig, Hive, et cetera. They have their own clusters, their own individual clusters, so there's a lot of replication of data. The scan rate that we've seen here typically is an hour will do about a month. All right, so now we're talking about a day or 2 for some of these queries. One thing that we've noticed across Amazon is, again, lots of teams have their own cluster. They're all unique. They're all different. And each team now has a lot of overhead in managing these clusters and managing the costs that go with these clusters. So what did we do? So we challenged the Redshift team, as well as the company challenged us to come up with a better solution. So we started off with a 100-node, 101 one master, 100 nodes, 8XL Redshift cluster. 100 is very much a round number, but it's above the cap we needed, about a petabyte. We are using 3 clusters, 2 for production and 1 for test. We are using the standard pattern of using manifests that point to subfiles and chunks that actually represent the actual data file. And we're using ETLM, which is custom IP, similar Informatica, for scheduling and job runs. One thing I want to pause for a second. I've talked to a number of people at this conference, and I want to share a best practice, which really probably deserves its own slide here. It's just one little line right here. A best practice that we've done for years, is we run multiple clusters and we apply our workload to each cluster individually. So we think about a data warehouse cluster as a simple box, right? So we have to have multiple boxes, right? We apply the same workload to each. So if one goes down, that's okay, right? We still have the other ones working, all right? We also have to make sure that we have a separation of test from development. I'll get more important for Redshift, we'll talk about that. So it really is important that when you're designing these things for enterprise needs, you have to have multiple clusters. Redshift does provide the ability to restore from backup, as you'll see from our numbers. It takes a while, right? So if you need to get your data to your customers, and in a data warehouse situation, you always do, you need to make sure that you've got high availability, which means multiple clusters. So I'm going to get off the stage here for a second and let Summer talk about our techniques, but I want to talk about the performance first, so really leading with our conclusions. So our goal was 2.25 trillion rows, that's 15 months worth of data in an hour. we can do that in 14 minutes. Just blistering performance. This is on our 100-node cluster. Loading 1 day, which is loading 5 billion rows. Again, the goal there was 60 minutes. We're able to do that in 10. And loading 150 billion rows, so this is a 1-month backfill for us. Our goal was 1 day. We got it done in under 10 hours. So what we're seeing here is the ability for Redshift to scale out massively, and it's getting significantly better performance than we even hoped for. So I'm going to turn this over now to Summer, who will tell you how we accomplished this leveraging Redshift.
Thanks, Eric. So quickly, my name is Samar Sodhi. I manage the data warehousing team. And this year, I've been leading the initiative of enabling clickstream data sets on Redshift. So just a brief outline of the talk. So I'm going to be covering the design the design aspects and following up with the benchmarks and the learnings we had from there, and following it up with much more granular performance the benchmarks which we found out. So so starting with so just to cover. Rather than covering the width of all the tables and the design aspects, we'll rather focus on the largest table we had. So the biggest table we have is a 400 TB table, which captures data at the lowest grain. And this table is growing really rapidly. So the key challenges we had with Redshift was the deletes are expensive. We'll cover that in a bit, like why is it expensive. The second is the data as you insert is unsorted, so you don't get the benefits of pruning at a block level. So what that results in is that your queries get slower with time. Just to give more idea on these 2 points, so as you delete a data set or a bunch of rows, in Redshift they get logically deleted, they don't get deleted actually from the disk space. So you have to actually run a vacuum operation to flush them through. So vacuum is a costly operation, processing intensive, and more so on a very big data set. On the unsorted data, when you are actually, so to get the benefits, so you don't have partitions in Redshift. So the equivalent feature you have in Redshift is called sort keys, and the data as it goes in is not implicitly sorted. So what this enables you to do is, the sort keys, that it actually allows you to go to the block level and actually prune it. Each block has information of the start and the end of the data set in it. So you can actually jump a lot of blocks and get to the right place. So that's the performance optimization. So this sorting doesn't happen implicitly. You have to run a vacuum for doing that. So this is costly. So that was one of the constraints we had. The next one was the locks on Redshift are at table level. They are not at row level, so you can't actually do concurrent parallel loads as you can do in Oracle with different partitions being there. So this is critical for us because we have a use case where you end up backfilling data for the past, say for last 3 months or 4 months. You can't, if you have to do it in sequence, that doesn't scale. The last constraint we worked around with is on the concurrency limits Redshift gives. We can have 15 concurrent queries running. You can move it up to 50, but those are mostly for the tactical queries. But if you want to do processing intensive workloads, that's pretty much capped at 15. So, and the other side effect there while discussing the nature of queries is that one bad query or runaway query can lead to a performance impact on the cluster. So how do you prevent that sort of a thing? Because the architecture is shade-nothing architecture. So to work around those limitations or the constraints we had, the way the table was designed was we had monthly tables underneath, and it was abstracted with a view on the top. What this enabled us to do is we could actually run vacuums much faster because it was happening on lesser data. You can actually sort the data much more faster. So there's a keyword used there called deep copy. Deep copy is pretty much synonymous with vacuum. It's a workaround to do vacuum in a faster way where you do you pick up the data again and insert into a new table. So while it's inserted afresh, it gets sorted implicitly. So And the other next advantage is you can do the loads in parallel because now you have monthly tables. So if you have 3 monthly tables, you can do 3 loads in parallel. The last is a slight optimization where you can, this is pretty much, it mimics the partitioning scheme in Oracle. So you can actually hit the partition or the monthly table right away if you have dynamic wildcards. So a table, say, is ABC underscore 2014-01. So you can hit the table directly rather than going to the block level for the pruning. So this approach, again, comes with some cons. So one, the first one, or the most important one, is mostly from the extract perspective. The queries running on it, they do not always, for all cases, do a predicate push. And it applies to 2 cases where you have a simple predicate push where you have a wait clause. It doesn't get always pushed down to the monthly tables. The second is the join doesn't get pushed down always when you to the monthly table or whatever underlying table you have underneath the view. The second one is you can't stretch the limits because it's capped at 9990, so which means that you cannot go for hourly partitions or hourly tables or daily tables. You can't do it for a bunch of tables. So you have to use it for specific use cases. The last one is not really a con, but is mostly from the operational perspective, is a maintenance overhead because there's no single handle on the table. So you have a bunch of tables underlying and you have to do all the maintenance activities for all of them, which is vacuuming and the stat collection and ensuring there's no skew on them. So you have to do all that for all the tables. So the next bunch of slides is going to be around the architectural best practices, which we learned while doing this project. So the most important one is the S3 chunk size. So this is where we could actually, while ingesting data into Redshift, we saw 2x performance benefits. So the best way to ingest data into Redshift is via S3, especially if you're doing it with big volumes. What plays a critical role is what's the smallest quantum file you use while ingesting. What we have been using is 250 MB. This is not something which will fit for all. So the guideline here is you can actually go up to 1 GB for one slice. When I say one slice, it means this 8 Excel machine has 16 cores, so 1 core is equivalent to a slice. So each slice can take up to 1 GB. But then this also depends upon the type of workloads you have. If you're just inserting or merging, say, 5 MB of data, then you might not want to have a limit which is 1 GB. And it also depends, the other guideline here is you should be ensuring that all your slices are equally working so that the implicit parallelism is actually being leveraged. So if the next one is distribution key. This we distribute on a session ID. It's an optimal call between the skew it causes and what's the usage pattern you have. So this again impacts the loads if you are working with merges and all that, so that you're not spiking the I/O on just one of the nodes, or you're not spiking the CPU on one of the nodes. So it distributes it equally. So compression at column level, use it. Coming from Oracle background, this is not really obvious, but we could see a performance, not performance, but space optimizations up to a degree of 3x by doing columnar compressions. So it gets a little tricky because you have a lot of options there for the column level compression. So what we use is we load the data into a table as it is, and then we run analyze compression on top of it. And Redshift, this tool gives you the suggestions for the best compression scheme to use. The next option you have is as you load the data from S3 using the copy command, there's a switch there for called compupdate, which will implicitly give you the best compression scheme. So we don't really use that because that is fast, but it's not optimal. It does a random sample on the data. Analyst compression is much more intensive, takes more time, but it is something which should be using for bigger tables. Collection of stats. So this is an interesting one. This was a discovery we did. So if you have a table with, say, a column which has 10 distinct values, or let's say 9 distinct values, what Redshift does in the backend is it stores the count of these values like how many values you have for each of these 9. And this is really critical from the performance perspective, because everything is driven from cardinality backwards. You have the execution plans, which the type of join or the sequence of join is backwards from the cardinality which comes up. So if you have 9 columns and insert the 10th value and you don't run the stats, as soon as you load, what happens is it assumes the cardinality to be 1, and that pretty much the whole execution plan gets messed up. So you should be actually, if you have a column which is having cardinality less than 10, you should actually be collecting stats as soon as you load them. For the other tables, you can actually go in for collecting stats at table level once in a week. And for columns, so you can collect in Redshift, you can collect stats at the column level, which is much more cheaper. It's almost 50x cheaper. So if it takes an hour or so to load to collect stats at the table level, at column level, you can collect it in a minute or so. And which is much more effective, especially from the querying perspective. So we do collect stats at column level much more often, which is 3 times in a week, and at a table level, which is much more costlier once in a week. Next is, I think Eric touched upon it a bit, how do we ensure that operationally these clusters are stable and performing optimally, which is, we do that by, first up in production, we have 2 clusters, which not only ensures the contingency, but also allows for load balancing. And we segregate that from the test cluster, which is where people can test out their stuff, and based on imperative data, we qualify that job to cut over from test to production. So this ensures that query is not actually harming rest of the cluster. The second is more of a reactive approach we use, which is we have reapers which are capped upon runtimes, and if it goes beyond a point, beyond a specific runtime limit, it gets killed off, and the user is intimated around that. So this is a critical one. One of the important things in warehousing is how do you ensure your data quality is intact, especially with cloud, because there are a lot of moving parts here. You have S3, you have Oracle in the prod network, and you have Redshift, and you have the network in the middle. So what we do is, so while you're doing the ingestion or while you're taking the data out, which is the unload, ingestion is the copy, there is a function you can call which gives you the row counts which got inserted or got pulled out. So you can actually store it in metadata and tally that across. This ensures your data, what got pulled out is the same as what got inserted or got merged. One of the learnings we had here was we were using a data dictionary table, a metadata table called unload log, which is not really an authentic source to pick up that data. It's not really credible. So we moved away from that and started, so we went to these function calls. So this table is more for retrospective analysis than for operations. Next is the column level security. So this one is, in Oracle, you have the luxury of having security at the column level. In Redshift, you can have security at the table level, but not at the column level. And you don't have UDF support, so you can't actually encrypt those columns. So you do have support for SHA-1 and MD5, which are more of hashing functions. You can use them compositely, but they can afford you at max a weak algorithm for compression, for encryption. So what we do is we actually have a separate schema which is secured and which has the raw column as well as the encrypted column. And the encrypted column is the one which gets stored in all the fact tables and dimensions. So you can actually look up the right people, get access to this secure schema, and they can look up the stuff. So we've been using, so varchar and char are not exactly the same as they are in other databases. Var is limited by the number of bytes. So it is a single byte, and the char is, char is single byte and varchar is multi-byte. So if you go in for char, if you have UTF-8 characters coming in, it's going to pretty much fail. So you have to be really sure about it. So we actually suggest not using it. It's not worth the performance benefits it gives you. It is low on storage, but storage has never been a concern with Redshift for us. But if you are going with a char and you move to varchar, it's not as simple as an alter command. So you have to actually rebuild the whole table. So it's much more cheaper to take the right decision call at the beginning. The next is the query level best practices. So these practices are backwards from a few of the limitations that Redshift has. We pretty much saw that, we'll cover those in the next slides though, but that there's pretty much no query which we could find which was not tunable, but the approaches were slightly different here for this architecture. So when you have complex SQLs, you have SQLs which have more than say 10 joins and joins happening on functions. What happens is, again, the cardinality gets tossed around, and because of that, you have data being broadcasted, which should have been joined locally itself, or the order of join is all messed up. So the way to work around this is, if you have a join between tables A, B, and C, you actually join A and B and load into a temp table. This ensures that sequence is intact, and then carry that forward. So the right cardinality is cascaded all the way through. So this also fixes the problem in case you're using functions for joins. At times, we were observing that if you're joining on a function, the net cardinality after the join is really not what you expect it to be. It's really off from the estimate. The next one is the sort keys in the where clause. So if you're using a sort key, you expect the pruning to happen at the block level. It doesn't really happen if you use functions on top of it. It's pretty much like the way partitions work in Oracle also. So if you're using something as simple as NVL or coalesce of something, which you can break it apart, you should do that. So they basically, if you're moving around stuff from one system to another, you need to be cautious with these things. The next is the case when statements. So this is a really odd case which doesn't happen often. So this is when you have a big nested case when clause in the group by. And if you remove this case when, the query starts running really fast. So the workaround here is again that you can actually have lookup tables which do these lookups for you rather than doing a hard coding in the code. So coming to performance, these are some of the generic performance benchmarks which we came to. If you see, the first one is, this is the S3 copy into Redshift 100-node cluster. And if you see there, so the first section, the y-axis is on the rows in billions. So it pretty much scales linearly, almost logarithmically, where the gradient keeps on decreasing as you bump up to 150 billion rows, which is pretty much in 10 hours, which is awesome performance. So next thing we did is we had a bunch of queries, 1,000+ queries, which were running in Oracle. We moved all these into Redshift and ran them as it is. For most of them, which were running for greater than 5 minutes in Oracle, which was where really the value for the buck was, we could see that Redshift was performing almost 90% of the time better than Oracle out of the box. So this was a key discovery. So mind you, we didn't touch the SQLs. There were no changes we did. It was as it is, ported. And for the shorter queries, it was pretty converse. We could see that almost for 60% of the cases or thereabouts, it was running faster, but for 40% cases, it was running slower. It was in fact slower than 15x for a lot of cases, which were really odd. These were pretty much the ones which we covered in the query best practices. So these queries were well-tuned for Oracle, not for Redshift. So another important aspect in Redshift is how do you ensure your cluster is healthy, and the housekeeping practices which ensure that. So the key one there is the vacuum, which is the costliest. So we did these tests on 8 Excel machines, and we did it in 40-node cluster as well as the 100-node cluster. We could see it growing linearly. It took something like 80 minutes on the 40-node cluster to 30 minutes. So this was for 6 billion rows, and where 80% data was unsorted. Stat collections were much faster. Again, we can see a linear pattern there. So provisioning is another thing which you might run into. So snapshots, the great thing in Redshift is the snapshots are always happening pretty much every half an hour or so. So when you're doing explicit provisioning, the snapshot, because it's incremental, it takes less than half an hour, despite the volumes you have. So this was pretty much, this was for almost 600 TB of data and took half an hour to just get the backup out or the snapshot out. The restore for the 48-node cluster, Took 48 hours for the 100-node cluster. I've maybe missed out the volumes there. It was for 700 TB, and the resize we did from 40 node to 100 node took 48 hours. That was for a little lesser data, which was for 400 TB of data. So how do these benchmarks, which are more abstract, translate into tangible benefits for our customers? And so these benefits are mostly in terms of earlier availability of data and faster runtimes for their queries. So one of the popular cases where Redshift really shone out was where nothing else was working for us. We were hitting into scaling limits. So a Pig was one which we were using for doing a 10 billion join to 700 million rows. And what we saw was a very pleasant surprise. We could see performance, the runtimes coming from 48 hours down to 1 hour. So that was great. For Hive, we could see that this was much bigger use case where we had 21 billion rows joining to 10 billion. We had a 3-day workload coming down to 2 hours. So this made our customers extremely happy. The third one was which we worked on mostly, because most of the workloads are actually Oracle oriented, is we picked up some 8 pipelines and we moved them across, redesigned them totally for Redshift. We brought down the runtimes from 90 hours to 8 hours, which was more than 10x performance. And significantly also, it improved our code readability, because the code we write for Oracle, because it's not implicitly parallel, is explicitly made parallel by writing more SQLs. So our code, actually, the SQLs which we fire got reduced by a factor of 3 in Redshift. So thank you very much.
All right, thank you. We've got about 10 minutes or so for questions. We're happy to entertain any you guys have. Yes? Sorry.
Yep.
So how's the network latency from where? Right. Okay, what's the network latency from a copy from like an EMR cluster to Redshift, Samar?
So we were actually not pulling data from EMR clusters to Redshift. It was mostly from Oracle prod network to S3. We didn't see significant latencies because we were using multi-uploads for S3 multi-uploads to S3. So you can actually go really parallel there depending on how much you want to go. Because it's multi-threaded there. Yeah. So just to paraphrase the question, so the weblogs, which could be Apache raw, you're saying the cleansing of those into much more structured data. Is that the question? So that's not something which we do. That's an upstream system which does that for us. Yeah.
There's.
You can do that also. There is JDBC support for that, but you can't really do that for terabytes or even GBs of volumes. You can do for a bunch of rows, but it's not something which even Redshift suggests. So one of the other things we do is that we don't have a single cluster. So we have multiple clusters across. So the way the ETL workflow works for us is we do the extract one time and we load it multiple times. So S3 is an intermediate which really helps, both from archiving perspective as well as enabling the whole workflow.
You got a question? Yep.
So it's much easier, it's much weaker, right? So it's much easier to figure out. So it's not really an encryption algorithm. It's mostly at max it's a hashing algorithm, right? Yeah, not really the replica, just the raw column and the encrypted column. So somebody who wants to look up the actual raw value can look up the value. So you have the credit card IDs, which are encrypted in the dimension table. And then you have lookup table, which has just the credit card ID and the encrypted value, encrypted and the raw value. So you can look it up, but only, yeah. So can you repeat that, please?
You don't store your data in Redshift for a long time. You just like load the big chunk.
No, we persist the data. We persist the data in Redshift. Yes.
What's your solution strategy?
We have retentions on tables based on how popularly they are used and what is the demand from the end customers. They want to do an analysis across YOY, then maybe table is 24 months. But most of the tables do not have retentions, which are merge like updates and insert, like order tables, shipments. They have all the retention. But for other tables, we do have retention. It's pretty much backwards from the size of the table. So if you have a really big table, we don't go in for 10 years of retention. So it's so all the data, one cool thing here is all the data is already backed up in S3. Yes. So one of the things this approach allows you is because you're having a separate monthly table, right, underlying the view, you can just drop that table off. So that's how the retention works rather than doing a delete command.
Well, one thing I'll just add to that is a thing we found ourselves getting into, and you guys might find this as well. While some of our tables, for example, weblogs, were not the authority of record, so we do delete those. There are other tables that we've become the authority. Right? So for example, all orders, it's in the data warehouse because the ordering system deleted data at some point. So we became the authority, so we never delete that data. We have a couple of tables like that. So Redshift is nice in that, okay, we're there forever. We can actually have a growth strategy.
Yes.
Yep.
Yeah. So even updates follow the same pattern. Anything you touch gets logically deleted, the previous row, and one more row gets inserted in the backend. So your scanning gets slower if you don't run a vacuum, or if you run it up. We do updates, yes. We do merges, merge equivalent of insert and update. So what do you mean by parallel load here? Yep. So that depends. So the loads for a table, they're all sequential because there's a table level lock, daemon lock, which happens. You can't do multiple loads on the same table. So, but what you can do still is you can have different tables and have a view on top of it. This enables you to still do the loads in parallel. Yep. Yes. That's why we use a time series view there. Yep. Yes.
Yep.
So there are still some workloads which are running on those. The plan is to deprecate those. Yeah.
So for those that are running, like how are you deciding what to run on ANI versus what to run on Redshift?
So one of the key discoveries here was what Hive does in general, or Hadoop does in the general, is it's not really great at joins because the data is randomly hashed out. It is like chunks going randomly, right? So 64 MB or 128 MB. Here you have conscious hashing of data happening, right? Deterministic hashing. So joins can happen locally, which is basically computers happening closer to the storage. In solutions like Hadoop, the data is again pulled out and resorted for the joins. So it's much faster for joins in general. But if you're playing around with unstructured data, which you have to clean up, which is already denormalized, I think that's where I think EMR excels. Yeah.
Yep.
Yes, that's one of the key things. So I didn't
Tomorrow's
fit that
question?
in. Yeah.
Repeat the question.
So the question is that is denormalization a better thing in Redshift, right? So I think, yeah, so the answer to that is yes. It is one of the best things Redshift affords us because in systems like Oracle, you can't do a really wide table because that leads to row chaining if you're doing updates a lot of time. So I believe there is, but that's a very big limit. That's a very high number there, but there is a number. But you can actually go in for really wide tables with the columnar compression, and so performance is really great that way. Its usability is better also. So just as a general rule of thumb, we could find very few, like the slide I showed you previously, almost 90% of the stuff out of the box runs fast in Redshift. And for the rest of the stuff, if you actually do the tweaks, which is refactoring the code, you can make it run as fast or faster. So there was nothing specific we could find, which was astonishing. We pushed it really hard, where we couldn't find a workaround to solve that problem. It's mostly faster. That's. We do have, so basically because we're coming from an Oracle background, we don't really have wide columns. We restrict it to less than 1,000, 1024 characters because Redshift, Oracle starts bothering you because of the row chaining. So we really didn't have a lot of use cases which had wider, like say, blobs or clobs sort of things. We didn't have those use cases. Yeah.
Just to harp on that, we'll get a second. For when we're looking at Oracle performance versus Redshift, and this is pretty much true of Oracle versus any columnar data store. So Oracle excels when you're basically doing a lookup, right? It's got tons of indices. They do that really, really well. So when you're looking up individual values or you're scanning a small partition, it's great. The nice thing about Oracle is that it's fairly flexible. It's hard to do a query if you're doing lookups that will perform poorly, but none of them are ever blindingly fast. So this is where we saw the fast performing queries were great. And when we saw them performing poorly in Redshift, it's because either the default distribution key or the sort keys weren't sorted out in a way that would optimize for the query. So you can rewrite your table so that your query will be fast, right? But the point we make is if you're doing a migration from Oracle to Redshift, your long-running things will generally work fine out of the box. You don't need to do anything. But the horde of short-running queries, you got to refactor that, and you're not going to get a whole lot of gain because you're going from 5 minutes to 4 minutes. So, yep.
So I don't know if you get the way answer this, but do you know if there's plans to release more of the Postgres function support in Redshift? Right now, this is pretty bare bones.
So watch me tap dance. We don't have that great insight into the feature set. I know they finally released Median. We were really happy about that.
Yes.
We've been yelling at them for quite some time. We've provided them a list of all the missing support from Oracle PL SQL that our customers use. Basically a nice histogram order of what our customers use most common. They've done a decent job knocking that out. So we've got row count, we got median, we got a bunch of the reg expressions ones. But I don't know what their roadmap is.
Do you know anything about multiple sort keys?
No. Yep.
Did you select the number of nodes in your test case or in your environment based on the amount of data you had or based on the performance? And can you talk a little bit about how you made those decisions?
Right, so the question is, how did we pick 100? Was it based on storage or was it based on performance? It was primarily based on storage. Roughly speaking, for an 8XL, you can think of that as 10 terabytes worth of actual usable space. And so we needed roughly a petabyte. We've got what's 400 terabytes for the main table. We've got a couple other 300 terabyte tables there. And we want to kind of size so that we're not resizing the cluster all that often. So that's where we went for that. I think we have time for like 2 more questions, and then we're going to turn off the bell.
Yep.
Yep.
So you said that you have 2 production clusters and 1 for testing development. How does it work to have 2 production clusters? Is it like a master slave scenario or distributed?
So the question is, how does it work to have 2 or more production clusters? The way we work is we have files called load files, and we apply them equally to both, or to 3 or 4 or 5, or for Oracle class up to 10. So,
yes, it goes to one of them.
Yeah, first
one
available.
query goes to just one of the clusters, but they get distributed equally.
There was 2 questions. Yep.
How would you use Redshift if you were on, say, more disparate sources? Say you have like event server logs, firewall logs, and a couple other sources.
So the question is, how would we use Redshift if we're analyzing disparate sources? Well, we do that right now, and really it's a matter of figuring out how you're going to join the data up front, what the common keys are, and then getting it into the right relational structure to do that. So again, we have, at Amazon, we have a thing called an ASIN, which is the product ID for anything you buy. So typically a click will have an ASIN, and then anything that we make an order or a shipment, that ASIN's tagged, so we join through that way. All right, I'll tell you what, we're out of time, but we'll stick around here afterwards. Thank you for attending. Appreciate it.
Thank you.